Okay, we're going to continue looking at sequences, and now we're going to look at some more challenging ones. Many of these are adapted from problems from our book, so you'll probably be looking at some of these. So here's a sequence, a sub n equals 1 plus 1 over n to the n. And as I've been doing, sometimes it's helpful to put in numbers just to get a sense of what's going on. Here what you can see is as n gets bigger, I'm starting to get fractions raised to a power. And notice, like even if I skip to my 100th term, I get 101 over 100 raised to the 100th, which is kind of close to like 1 to the 100th. Okay, but remember, it's not exactly 1 to the 100th power, but it would seem like maybe these terms are getting close to 1, right? 1 to the 100th. But let's look at L'Hopital's rule, or let's take the limit as n goes to infinity, and you may remember that 1 to the infinity is actually an indeterminate form from first quarter calculus when we were talking about L'Hopital's rule. But for this one, in order to use L'Hopital's rule, we have to manipulate this a little bit. Recall, for L'Hopital's rule, it has to be an infinity over infinity or a 0 over 0 limit. So the trick is we have to get this n down out of the power. And one way we know we can do that is if we introduce a log. And so the way we do this, we've done this trick at several points in calculus, especially in first quarter calculus, is to rewrite this expression as e to the ln of 1 plus 1 over n to the n, taking advantage that e and ln are inverse functions, and what's always true is e to the ln of whatever you want, x, is the same thing as x. So we're taking something like this and rewriting it as e to the ln, okay? And the reason we're doing that is so we can bring this n down in front. And in order to take advantage of L'Hopital's rule, we need to get a fraction here. We have a multiplication problem, so that n is now going to move to the denominator as a 1 over n. So the n started here. By the property of logs, we can bring it down here, and then we're just going to rewrite that n as 1 over n in the denominator. Now, if we look at the limit as n goes to infinity, where in the exponent, n's going to infinity, we have the natural log of 1 plus, this is going to get closer to 0. The natural log of 1 will go to 0, and 1 over infinity will go to 0. So in the exponent here, we have a 0 over 0 limit, which now means we can use L'Hopital's rule. And so we take the derivative of the top, which the derivative of ln of stuff is 1 over the stuff times the derivative of the stuff. Of course, 1 would have a derivative of 0. 1 over n, also known as n to the negative 1, would have a derivative of negative n to the negative 2, which could be rewritten as negative 1 over n squared, which is the exact same derivative as this denominator right here. So these two are going to cancel out. And if we now plug in infinity to what's left over, this will now approach 0, the 1 over n. So we end up with just 1 in the exponent. So this limit is just going to be e to the first power, or just e, which means this sequence converges to e. That limit may have seemed familiar because it is kind of an important limit, and in first quarter calculus, it's typical to spend some time on this limit and know that that limit is e. So what we can actually do, and the book does this too, our 21C book, from now on, if you see a limit that has that form of 1 plus x over n raised to the n. So it's not always, it's the one we did was x had a value of 1, but whatever this number is right here, that will end up being your power of e. The answer is going to be e to the x. And it is given in our book. So all the L'Hopital's rule that we did on the previous page, if you know this, in 21C, it's usually fair game. You can just use this. You don't have to do all the work. If you see a limit of this form, you just go ahead and say it's e to the x. Okay. So here's another example related to that. My sequence is n times the ln of 1 plus 2 over n. I'm not going to write out any terms. I'm not sure I would learn much from that anyhow. But if I take the limit as n goes to infinity, this limit has the form of infinity times, if n goes to infinity here, this term's going to go to 0, and the natural log of 1 will approach 0. So this limit has the form of infinity times 0, another indeterminate form that we know from first quarter calculus. So here what we're going to do, we're going to manipulate this, and now that we know this formula up above here, what we're going to do is actually take this n, and because it's in front of a log, it can go up in the exponent. And from what we know up here, 1 plus 2 over n raised to the n power as n goes to infinity is going to approach e squared. So this just becomes the natural log of e squared, and those are inverse functions. It's just going to be 2. So this sequence converges. This particular limit that has e in it there's a lot of examples in the book that involve that special limit. So you want to be on the lookout for that one. Here's another one that's kind of a sneaky one. Okay, my sequence is n over n plus 3 to the n. If I took the limit of that would have the form, the inside is going to approach 1 because your powers of n are the same, raised to the infinite power, which is an indeterminate form. So what I'm doing next is trying to manipulate this so that it has the form of that special limit that involves e to the x. So what I'm going to do is flip the inside. I'm going to take the reciprocal of the inside, which is, if I do that, that's the equivalent to raising that to the -1 power, right? So this is the same thing as n plus 3 over n to the -1 power. Why did I do that? Was so that I could now have just one term in the bottom. And when you have one term in the bottom, we can split this fraction up into 2 pieces. N over n is 1 plus 3 over n. So that's the inside. And then all I'm doing here is I'm just trading places. Your properties of exponents, if I have a -1 here and an n, I could switch those. It's the same thing. And now I can see that this limit right here is approaching e cubed. Right? It has that form. And it's being raised to the -1. So my limit would be e to the -3, which means my sequence converges. So there's a few examples, all related to that special limit involving e. So that's one to be on the lookout for. All right, that's all for this one.